Hi Math 111. In this video we're going to introduce section 12.1 where we talk about sequences and summation notation. So let's start out with a definition of a sequence. A sequence is a function whose domain is only positive integers. So this is just a fancy or very specific kind of function. Remember that a function has an input and an output, and for a sequence, this is a kind of function, but its inputs are only allowed to be positive integers. Remember, positive integers are 1, 2, 3, 4, 5, 6, and so on, right? So we're only allowed to plug in the counting numbers. Specifically, a sequence is going to represent really an ordered list of numbers, because when you plug in 1, it's going to give you an output. When you plug in 2, it's going to give you a different output. Plug in 3, different output, so on and so forth. So the outputs are arranged according to what the input was. You know, when 1 is plugged in, that's considered the first input, right? And it would give a corresponding output. That would be the first output, and so on. So the sequence represents an ordered list of numbers where each number is the result of inputting an integer, we should say positive integer, into a function, right? That should say positive integer. Okay, because this function only allows integers to be inputted, we don't use x as the input variable. The reason for that is because x usually denotes for us things. It could be decimals, it could be fractions. That's just more of an intuitive kind of thing, where for us, if we use a different letter, that kind of reminds ourselves that we're only allowed to input a positive integer. So instead, we'll use the letter n as our independent variable. Remember, the independent variable is the input into the function, right? So for example, we could consider the following to be function notation representing a sequence. So the function is f of n. Again, it's an n because we're looking at this as a sequence. N is allowed to be a positive integer, 1, 2, 3, and so on. That's what the dots mean. And the function says that the values of the terms of the sequence, the outputs of this function, are going to be determined by this rule. Remember, this rule says when you plug in n, the output would be 1 over n, right? This is what's going to be called the reciprocal function. We'll talk about that more when we do our library of functions. Okay, so this is really the function f of x equals 1 over x, but again, we're only allowing positive integer values to be input, right? And 1, 2, and 3, and so on for the input here. So instead of f of x, we're using f of n to remind ourselves of that. So using some set notation, we could show that the function would look like this. We would say when you plug in 1, it gives me 1 because 1 over 1 is 1. When I plug in 2, it gives me 1/2. When I plug in 3, it gives me 1/3. But instead of having all of this sort of ordered pair notation like this, which kind of gets a little bit redundant because we know that if we instead wrote it like this, we know that this first number right here is the result of 1 being plugged into the function. This second number is the result of 2 being plugged in, because we know specifically for a sequence that we're only allowed to plug in these positive integers right here. Okay, so we know that this first number is f of 1, this is f of 2, this is f of 3. Okay, so this is sequence notation. Okay, and again, because we assume that this first term or the output value here corresponds to the first input value and so on, it becomes clear and we don't have to use this ordered pair notation or even the function notation. Okay, we also label these numbers that are listed here as an ordered list. We label them as terms of the sequence so that we can refer to them later. The first term of the sequence is labeled A1, that equals f of 1. The second term is A2, which equals f of 2, and these are subscripts, by the way. This is A sub 1 and A sub 2. Okay, and if we kept going out and out and out and out and out, we could say whatever term we want, like the nth term, right, of the sequence is labeled a sub n, which equals what happens when you plug in n, right? So for example, the 50th term is labeled a sub 50, which is when f of 50 happens, okay? The nth term, really, the description for it is equivalent to knowing the formula for the function f of n. So up here, this is really 1 over n. That's the description for the nth term of the sequence, right? It's another way to write the sequence, really, if you know this formula for the function, right? If you know what the description of the nth term is, okay? So another way to write the sequence is to simply use this notation down here with the squiggly bracket set notation. We could say that the sequence, the terms of the sequence, are determined by using this formula right here. And I know this looks a little bit maybe lazy because the squigglies are supposed to be for a set of things, right? Well, this does denote a set of things because notice we haven't said that it's a specific n or anything like that. We're saying for all possible n, this is what the sequence looks like, right? And again, we're assuming that n is allowed to be 1, 2, 3, 4, 5. So that means right here, this notation is equivalent to writing out this notation here, this ordered list of numbers, 1, 1/2, 1/3, 1/4, 1/5, 1/6, so on and so on. Okay, it's just a sort of compression of the notation a little bit. So the way we've just described this sequence here is by using the explicit formula for the nth term of the sequence. We've just basically discussed describing it using a formula, right? It depends upon which term of the sequence you want to find. So if you want to find the 50th term of the sequence, you plug in 50 into the explicit formula here. Instead, we don't have to define sequences like that. We don't have to define a sequence where if you want the 65th term, you plug in 65 into some formula and it gives out the term of the sequence, the 65th term of the sequence, which is 1 over 65. Instead, we could describe a sequence where the value of the next term depends upon the value of the current term. And this is the idea of describing a sequence recursively. Okay, this means that the value of the next term depends upon the value of the current term. In order for this to work, of course, you have to be given the first term of the sequence, right? You can't say, I know the value of the next one if you don't know what the value of the current one is, right? You have to have a starting place, okay? So how would we write this? Let's see what it would look like. We can use sequence notation again, right? And the idea here is that the value of the nth term of the sequence, that's that a sub n, remember that's the nth term of the sequence, the value of the nth term of the sequence is equal to what? Knowing the value of the n minus 1th term, the one right before it. Yeah, that n minus 1 just means the one right before it, the term right before. Yes? So if you know the value of the n minus 1th term, you plug that into some rule and it gives you the next term. That's the idea. So let's look at an example. So here we have, this is a recursive definition for a sequence. We know that a sub 1 is 5. That means the first term of the sequence is 5. Yes? We're told that if you know the n minus 1th term, then you get the nth term by doing what? Adding 1 to the n minus 1th term. Yes? So for example, if we know the first term is 5, how do we get the second term of the sequence? Well, let's go down here. So the sequence is found by calculating the terms. Remember, the first term is 5. That's given to us. The second term, remember, is found by doing what? Because we have a recursive definition, the second term, a2, is equal to 1 plus a2 minus 1, which is a1, right? Yes, here. So that means a2 is 1 plus a1, but we know what a1 is. It's 5, right? So that means I do 1 plus 5, which is 6. So a2 is 6. How do I find a3? a3 is 1 plus a2. It's the 1 plus the previous term, which is 1 plus 6, which is 7. So the sequence looks something like this. 5 is the first term, 6 is the second term, remember, because it says to do what? Add 1 to the previous to get the next. 7 is the next. What would be next? 8, and then 9 and 10 and so on, right? That's a recursive definition. Okay. Sometimes a mathematical operation you may experience when you're doing these sequences is what's called a factorial. A factorial is just a specific mathematical operation, and it uses this exclamation point right here. So this says n factorial, and it's defined by doing the following. To find n factorial, you multiply, I guess you take the n, this is the best way to describe it, you take the n and successively multiply by subtracting 1 every single time until you get down to 1, right? So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Okay, 100 factorial would be 100 times 99 times 98 times 97 times 96, all the way down to 1. Okay, these numbers get really large really quickly. There is a factorial button on your calculator. If you go to Catalog and then go up into the symbols, you'll find the little factorial symbol, the exclamation point. It's also in your math menu, so you can play around with that. We'll talk about this in class 2 and help you locate it. But that can help you quickly calculate factorials if the numbers get large. But quite honestly, if they're smaller like this, it's not too difficult to just do them by hand. Okay, but sometimes you'll see this factorial used to define a sequence, and that'll be good for us to know for later as well. Okay, so once we have a sequence, what we can do is take the terms of the sequence, these are the terms of this sequence, for example, 5, 6, 7, and so on, and we can, instead of just listing them out like this, we can actually add them, right? So we could say 5 plus 6 plus 7 plus 8 plus 9 plus 10, and keep going and going and going and going, right? We're going to need some notation to do this, just like we needed new notation to describe the sequence. So to add the terms of a sequence, we can do the following. We can write this. Okay, it looks a little scary. Don't get nervous. It's okay. So to add the terms of a sequence, we write first term plus second term plus third term plus on and on and on and on and on, plus however many terms you'd like to add of the sequence, right? The sequence may go on and on and on and on and on. You might just want to add the first n terms, let's say. All right, but this process can become kind of tedious, right? If we wanted to add up 100 terms, that gets to be a lot of addition operations. So instead of writing out A1 plus A2 plus A3 plus A4 plus A5 plus A6 all the way up to A100, we can compress that notation and make use of what's called summation notation. Okay, so we can denote this sum here, A1 through AN, by using this notation here. Okay, and this is called summation notation. The symbol, this big E thing, this is actually the Greek letter sigma, and it's an instruction to add things up, right? Add some stuff. Okay, it means add in mathematics. And what are we actually adding? Well, the thing that's written here to the right, that is the stuff we are adding, right? It says add up the terms of the sequence. I know it says AK instead of A1 or AN or all those kinds of things. That K is just called the index, and it tells you what terms of the sequence to add. So it says you're adding up terms of the sequence. Which terms are you adding? Notice it says go from K equals 1 to n, right? That's what these notations here are for. It says start at k equals 1 and go up to n. That might be hard to see that that's an equal sign, but it is. Okay. So in an example, we're adding the first n terms, right? We're adding the first term through the nth term. So it's this expression here. These two things, the left and right two sides of these are equal, right? They mean the same thing. Okay, add up the first n terms, add up the first n terms. Usually, by the way, remember we will have a rule for figuring out the value of the terms of the sequence. So for example, like our 1 over n, we'll have a rule for that, right? So for example, you could maybe see something instead of this abstractness over here, you might see something like this. You could see a sigma, and it would say add up the terms that are described by that rule and start at k equals 1 and go to 5, right? And what would this look like? Well, it would say add up the first, second, third, fourth, and fifth terms because we're going 1 through 5. So the first term of this sequence would look like what? That's when you plug in 1, right? Because the rule says to calculate the terms of the sequence, you do 1 over k. So we start at k equals 1, plug in 1. Now this is the second term of the sequence, right? This is a sub 1, this is a sub 2, and then we keep going, right? A sub 3, and then a sub 4, and a sub 5, right? And of course it says plus, right? It says add all these things together, plus, 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 plus. Okay? That K thing is called the index, like I said. So at this point, what I'd like you to do is pause the video and read example 7 on page 808. Once you've read that example, then come back and we'll continue and finish what we're doing here. So welcome back. I'm assuming that you have read example 7 on page 808. It's not very long, but what you've hopefully noticed is that this notation is really useful if you're adding up lots of terms of a sequence, right? The addition will result in a real number. You're adding up real numbers. So for example, like the one I wrote over here, you're adding up 5 numbers. This is going to result in a real number, right? Okay, but if instead I change this 5 to 100, right, then it says you're adding up 100 numbers, right? You're still going to get a number, but it can get a little bit tedious, and like I said before, this notation is really useful instead of writing out the first 100 terms like this. Okay, luckily, to figure out what the value of this sum actually is, there are some formulas that we can make use of. There are some addition formulas in our textbook. So what I'd like you to do is see the theorem boxes that are on page 809 and 810 in your text. If you're using the electronic version of your textbook, this is the same page numbers. So just go ahead and open up a new window, pause the video, and look at the theorem boxes on page 809 and 810, and they will show you how we can actually use this summation notation to arrive at the value of a sum of a sequence, right? If we're adding up lots of terms. Okay, those formulas are really helpful instead of actually performing the arithmetic of adding them all together. Okay, so once you have looked at those theorems, then what I'd like you to do is please read example 9 on page 810. Only read the algebraic solution. Don't worry about doing the graphing solution that's in the right-hand column. Okay, once you're done with that, then you are all set watching the video. Sorry, this one pushed over 14 minutes. I'll see you in class.